thought I was early, and then I cleaned the board, and all of a sudden I was late. Anyway, I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. Thank you again for these students. Just ask you to guide our steps today. Help us to glorify you in what we do. I pray the students, if they're struggling, you'd encourage them just to do their best each day, Lord, for your glory. In your name I pray, Lord Jesus. Amen. Okay, so any questions? Okay, so one of the things I mentioned is I owe you a proof of the laws of logarithms. So what were the laws of logarithms? Laws of logs. What was it? If a is not equal to 1 and a is greater than 0, and if x and y are positive, then log base a of x times y is log base a of x plus log base a of y. We also have that log base a of x to the power p is equal to p times log base a of x. And last but not least, we have the log base a of x over y is log base a of x minus log base a of y. All right? So I thought it would be good for me to prove these things, since I've just asserted that they're true, but I never really explained to you why they're true. So let's try to prove them. All right? So what I'm going to do is I'm going to start with, let me call this number 1, number 2, number 3, okay? Number 1, number 2, number 3. So let's start with number 1. So I'll start with log base a of xy. All right? And then what I'm going to do is I'm going to make a sneaky trick. And the sneaky trick I'm going to do is to rewrite that as log base a of a to the log base a of x times a to the log base a of y. I can do this because x and y are positive, right? So this is an identity which is available. We can always rewrite a number as exponential of log of that number, like that. All right? And then now I've got, I can use the law of exponents, right? So like if I have a to something times a to the something else, I just add the exponents, right? So this is, using a to the s times a to the t equals a to the s plus t, right? That's one of our laws of exponents. And then what? Well, then I've got a log base a of a to the something, right? So by definition of log being inverse function to a to the something, that's just log base a of x plus log base a of y. And there you go. That proves number 1. So really, if you take advantage of the fundamental identities that we have for the logarithm, right? What are the two sort of fundamental identities for the logarithm are what? The one is that, a to the log base a of, let's say, y is equal to y for y greater than 0, right? The other is that the log base a of a to the power x is equal to x again. That's for any x. So I use both of those in here, right? I used like here, I had log base a of a to the something, right? And then I just put the something back down here. So that something is kind of behaving, instead of putting x here, I could put, like, I don't know, Pac-Man. There you go. And so you could think about This is what's underlined in red as being that Pac-Man. So a log base a of a to the Pac-Man is just Pac-Man again. That's the pattern there. Anyway, so there's the proof of number 1. How about number 2? How do we prove that? Number 2, I'll start with log base a of x to the power p, and I'll rewrite that as log base a of a to the log base a of x all to the power p, right? Like that. But the thing is that we know that if we have a to the s raised to the p power, we get a to the sp, right? That's a law of exponents. So I use that here, and that gives me log base a of a to the p times log a of x. See, because a to the sp is also equal to a to the ps. I mean, sp times ps. The multiplication commutes, right? Either go either way. It's just more aesthetically pleasing for me to write the p first. And then I go back, I go, oh, I got log base a of a to something again. Log base a of a to something, well, that's the something again, so I get p log base a of x. And that, my friends, is exactly what we wanted to show for number 2, right? That you can pull power out of the logarithm. We just did it, yeah. So this law of exponents implies this law of logarithms. This law of exponents implies this law of logarithms. And what's the number 3? Number 3, we can basically just use 1 and 2 to get that one, right? So if you look at it, log base a of x over y is what? That's log base a of x times y to the minus 1, right? But then applying number 1 and number 2, first of all, apply number 1. Number 1 gives me that this is log base a of x plus log base a of y to the minus 1, right, by 1. And then that is equal to log base a of x minus log base a of y by 2, with p equals to what? P equals to minus 1, right? So really, 3 is a consequence, a logical consequence of 1 and 2. If I know 1 and 2 are true, I get 3 for free. So anyway, those are your laws of logarithms. There's why they're true. They're really just reformulations, in some sense, of the laws of exponents, which we already know, all right? Now, earlier in this course, I proved, I haven't proved much in here, right? I proved, I think I proved the quadratic formula, essentially, right, by completing the square. And there, I think it's important for you to understand that proof, because I essentially ask you to repeat the proof in problem after problem after problem, where I say complete the square to find such and so forth, right? So you do need to understand that proof, for sure. This proof, it's good if you understand it, but this one I won't ask you to recreate. Like, I won't ask you to prove the laws of logarithms on the test. This is just for your informational purposes, all right? So this is something I think every math major should be able to do. But like a typical college algebra student, prove the laws of logarithms, no, that's kind of a little bit above your pay grade. So, yeah. So any questions before I get started in here with examples beyond these proofs? Nobody? All right, well, so we were looking at, we're looking at exponential, we were looking at finding inverses, right? So let's look at another one of those. Let's let f of x equal to, oh, I don't know, 2 plus, let's say, e to the x minus 4. So I have a couple of questions. A, is f 1 to 1? All right, and then part B, if f is 1 to 1, find formula for the inverse function of x. And then C, graph both y equals f of x and y equals f inverse of x. All right, let's graph both. So There's different ways to go about this problem. Like, how do you check if a function's one-to-one? What are our two methods that we had for that? The horizontal line test, right? Or we could use the algebraic test, right? So I guess the horizontal line test would be smart, because if we graph y equals f of x, then we can come back to it and add the graph of y equals f inverse of x for part C, right? So let's plan ahead and make our life easier. So let's go the graphical route on part A. Let's check by graph. Check by the horizontal line test. All right. So we're looking at y equals 2 plus e to the x minus 4. So what is this? This is y equals e to the x, and then we go y equals e to the x minus 4, right? And then we go to y equals to 2 plus e to the x minus 4. So what are those two transformations that I just wrote down there? This is what? We go right 4, right? And this one is what? Then up 2, right? So we just take the graph of e to the x, which is what? So it just looks like this. This is graph of y equals e to the x. Yeah. It's got a y-intercept of 0, 1. Right? And then that gets shifted over to 4, 1. Right? Like that. And then it gets shifted up 2. So let me try to make a big graph of this thing. I guess if I make it here, it'll be okay. I think if I just put it here, I'll still have room over there to work. Let me. Gah.
Would it be at 4, 1,
Poor planning.
2 from the,
Right 4.
and then do we go up 2 or?
Well, yeah, final. So that's the first step, and then the next step here. Yeah, you're fine. So 4, 1 would go up 2. So 4, 3. That point would go up to 4, 3. And the other thing to think about is the original e to the x has a horizontal asymptote of y equal to 0, right? And when you shift right, you still got the horizontal asymptote of y equals to 0, right? But when you shift up 2, the horizontal asymptote shifts up to y equals to 2, right? So like the graph, it looks something like this, yeah? Does that pass the horizontal line test? It does, right? So this passes the horizontal line test. So the answer to part A is yes, it's 1-to-1. It passes the horizontal line test. So passes H line test. So f is 1-to-1. That's important because we can't find the inverse of the function unless it's 1-to-1, right? You got some problems in your homework that's like ABC, right? And like part C is, I think, it's got like 2 choices for the formula for inverse function of x or something. And then I think part C is like the function's not 1-to-1, right? So that logically makes sense because either the function is 1-to-1, in which case you could find the formula f inverse of x for it, right? And maybe one of those 2 options, like A or B, is right. Actually, I think you're supposed to put the formula in there. Oh, let me stop trying to memorize your homework off the top of my head. But the point is, there's a homework question where you're either given the choice to put in the formula for the inverse function of x, or one of the options is the function's not 1-to-1, right? If the function's not 1-to-1, you can't find an inverse. Okay, that's something we should know. But this one is, so we can, right? How do we find the formula for the inverse then? And I'm discontent with my graph here, so I'm going to redo this bigger for part C. So poor planning on my part. I should have left myself like a lot more room to do this. Oh well. So part C, or rather part B. Remember the 4-step process. Number 1, we write y equals to f of x. Here f of x is 2 plus e to the x minus 4. Remember? Step number 1, write y equals the f of x. What's step number 2? We solve for x, right? Now, I guess we haven't done an algebra problem like this yet, have we? But we can do it, right? How do you solve for x? subtract 2. That's a good starting move. So y minus 2 equals to e to the x minus 4. Now I've got an exponential. How do I get rid of the exponential? What do I do? I take the natural log of both sides. Very good. So the natural log is the natural enemy of the exponential. They will annihilate one another in this sense. When you compose them, they go away. And then, one more step, we just have to add 4 to both sides, right? We get x is equal to 4 plus the natural log of y minus 2. Right? Now, I don't know if you guys remember or not. I think when I introduced this, I said, well, you do some algebra and then you find x equal to stuff and y, right? This is what I was talking about, stuff and y. Remember? I called it stuff and y. It's very academic, scholarly phrasing. There you go. And that's a joke. So I have to explain it's a joke. I guess it's not a joke. Oh well. This was f of x, so this guy here is f inverse of y. That was my step 3, right? Just labeling whatever that I come to as the inverse function of y, right? Now we don't want inverse function of y. We asked for the formula for f inverse of x, so I got one more step, step 4, which is what? Step 4 for me, f inverse of x is equal to 2 plus the natural log of x minus 2. There you go.
Wait, where did the 4
Did I? Oh, yeah, my bad. That was a 4. Thank you. It's kind of interesting, right, to compare the formula for the function to the formula for the inverse function, right? They both involve 2 and 4, but kind of in a reverse fashion, right? There's something kind of pretty about the mirroring of the formulas here. Now, I should say more. What can you tell me about the graph of this function? So I would think about this as follows. So we take y equals natural log of x, right? Shift to right, then up 4. Up 4, right? All right, so let me try to graph everything over here. I'll do it real big. Let's see here. So my important things that are going on are, let me just make myself some dotted lines to try to keep things accurate as I can here. I'm going to do a dotted line at 4, a dotted line at 2. Because I think everything interesting is happening at 2. X equals to 2, x equals to 4, y equals to 2, y equals to 4. All right. Let's see here. Let me graph the exponential function over there. So let's see here. 4, 3, it's like here-ish, right? That's 4, 3. And let's see here. What is f of 0? What's the y-intercept for? Sorry, having a moment of. Wait, how? What? Sorry, I'm confused all of a sudden. That's just reference. Those aren't vertical asymptotes. Sorry guys, I'm troubled because it seems like when I look at f of 0 for this function, I get 2 plus, when I look at the function, right? F of 0 is what? 2 plus e to the what? Oh, not e to the 0, it's e to the what? E to the minus 4, yeah? That's not 2. It's really close to 2, but it's not 2, right? That's like 2 plus 1 over e to the 4th power. E is like 2.7. That's really like about like 0.04 or something stupid. It's really small, but it's not 2. I was thinking, here's the thing that was wrong in my mind. I was interpreting that as e to the 0, which was giving me a y-intercept of 3, which I couldn't process because I'm at 3 over here. I knew I wasn't at 3 at the y-intercept. So I'm like, what? It's actually down here. Okay, it's really, really close to the y equals 2 line, right? At the y-axis there. And so here it is. We have something kind of sort of like that. All right, there's my y equals f of x. So that's not I don't mean the horizontal dotted line there to be a horizontal asymptote. I was just doing it for reference. Okay, like the horizontal asymptote for the function is just, if I do it in green, I can do it in green, right? So the horizontal asymptote is just this. That's the horizontal asymptote. Y equals to 2 for, f of x equal to 2 plus e to the x minus 4. All right, so there's the graph of the function again. I just made it bigger. Okay, same graph. What does the graph of the inverse function look like? So there, I do have a vertical asymptote. When you plug in 0 into the natural log, that blows up. All right, so that's what becomes large and negative. And so like we have a vertical asymptote at 2 for the natural log, like this. That is true. This is actually a vertical asymptote for the inverse function. And we can use our usual bag of tricks here. So like this point is what? What do we say? 4, 3. And this point over here was 0 what? 0, 2 plus e to the minus 4. So we could track those 2 points. We can mirror those 2 points on the inverse function, right? Because the inverse function has the same points, but with the x and the y flipped, yeah? So like this point becomes 3, 4, right? Where's 3, 4? Well, 3, 4 is up here, isn't it? Yeah? That's this guy. And where is 2 plus e to the 4th, comma 0? That's like here-ish, That's there. Yeah? And so what we got is a vertical asymptote like this. Comes up through this point, comes up through that point, and then bends like that. So something like that. If I did it right, they reflected one across the other across the line y equals x. So I think there will be a point somewhere out there where I think there's going to be 2 points where they cross if I've done this graph right? Like there are 2 places where the function's equal to its inverse, one here and one there. How would you find those points of intersection between the graph of the function and the graph of the inverse? What would you do? Yeah, exactly. To find points of intersection, we need to solve f of x equals to f inverse of x, yeah? What would that look like? We'd have to solve 2 plus e to the x minus 4 equal to what? 4 plus the natural log of x minus 2. You can look all through your homework. You will not find such a problem. The reason for that is that cannot be solved by elementary means. So this requires what's called a numerical method, which is a fancy way of saying the only way you can solve this is basically with a computer and just kind of looking at the graph and doing things like that. The thing is, like, I'd like to isolate it. So here's the problem with this equation, right? If you isolate the exponential, what happens? If you isolate the exponential here, then you've got a natural log plus a number on the other side, right? How do you get rid of the exponential? Then you take the natural log of it. And then that gives you, you know, x minus 4 equals to the natural log of something plus something else, which is not nice. And then to get rid of the natural log, you take the exponential. But then you're like back where you started again. It's just no good comes of that equation. So my point to you is, just because we can solve a lot of equations here doesn't mean we can solve everything. It's not that hard to write down an equation that you can't solve using the methods in here. Here's one, much less sophisticated. Suppose you want to think about the line y equals e to the x, right? And you're interested in where does that cross the line y equals minus x? What's that point of intersection? How would you solve that? I mean, you'd solve it just like we were just talking about, right? You set e to the x equal to minus x like that, you know? But how do you solve such an equation? See what happens if I take the natural log, what happens? Well, first of all, I can't take the natural log of that. Why? Why can't I take the natural log of that equation? Well, I can, I guess, but I have to be careful. We can only take the natural log of a positive quantity, right? So when could I take the natural log of minus x? What would I need to know about x in order to take the natural log of it? I would need that x is negative, right? So if x is negative, then minus x is positive. So you could do that, you know, if x is less than 0, then we have natural log of e to the x equals natural log of minus x. Great. Now this gives us x, and then we've got equals natural log of minus x. So it's like, oh, wonderful. I've traded one problem I can't solve for another, right? And you can do this all day long. So you're like, oh man, I want to isolate the x, right? So how to get rid of the natural log? Well, take the exponential of both sides. Then what happens? If you take the exponential of both sides, what happens? Then we get back to e to the x equals 2 minus, oh man, well we come full circle back to where we started, right? And like, so we can do this all day long, we never get anywhere. So this kind of problem we can't solve. So hopefully I don't ask you any of these on the test, right? Yeah, I don't, like one of your jobs as college algebra students this is not one of the problems we know how to solve, right? Like we take that off your plate, right? It's not like I give you a problem and you're like, the solution is this, or another option is, this is not a problem type that we've covered, right? We don't ask you to figure that out, do we? Yeah, maybe you don't think about this, but this is the hardest thing of all, is knowing when the kind of problem you're looking at is actually one which is solvable using the tool set which you have available. So let's get back to those problems. So actually the solution to this problem does have, there's a solution to this problem in terms of something called the Lambert W function, but that's essentially just a name people made up for the numerical method that's used to solve this, for what it's worth. So let's look at week 12 homework. Can you believe it's week 12? I can't. So here we go. Let's look at example. Let's see here. I guess that was my example. I've lost numbers. Is that example 1? I think that was example 1. This is example 2, isn't it? It's a non-example, but there it is. So this is example 3. Example 3 is essentially number 2 from week 12 homework. And here it is. For me, it looks like this. Log base 4 of 36. We're supposed to rewrite this in terms of natural logs. How should we do that? Can you guys tell me? How do you rewrite log base 4 of 36 in terms of the natural log? Nobody? So I mentioned the change of base formula. Do you remember what it was? If we have log base A of whatever, let's call it Pac-Man, then that is the natural log of Pac-Man divided by the natural log of A. So this is one of the versions of the change of base formula. So if I'm going to, so this would be natural log of 36 divided by natural log of 4. And that is actually the answer for number 2 in your homework. They just want like a ratio of natural logs for that one, okay? Example 4. This is number 3 in your homework, something like it anyway. Here we're faced with the natural log of 1 over e squared. But I'll pause here. Are there any questions about the previous one? So the point of the homework is just to try to make sure you guys know about the change of base formula, basically. Why do you care about the change of base formula? It's because, among other reasons, you have natural log on your calculator, right? You may or may not have log base 4, right? And this one we shouldn't need a calculator for. How do we do this one? Yeah? Natural log of e to the minus 2, okay. And then what? And then they cancel out, right? So that is equal to minus 2. Because remember, natural log is what? Natural log is log base e. Okay, so there's that one. Let's go on here. I'll come back to like there's a couple problems on the Richter scale and decibels and things. I'd like to talk about those another day. I'm not going to talk about those today. Maybe Wednesday I'll talk about the Richter scale and all that. I'll skip ahead to number 7, which is, for me, it's like this. What's log base pi, log base pi of 42? This is an exceedingly silly question. Use the change of base formula to calculate it. And here they just want a decimal. So I would do, this is natural log of 42 divided by the natural log of pi. You guys know what pi is? You remember? 3.1415 blah, 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 blah. All that stuff. You remember? You remember? Yeah, 3.14159201745677. You remember? With that. Most of what I just said is a lie. The thing is, unless one of you guys actually has pi memorized past about 5 digits, I can make up whatever I want, right? So, I tried this once, and a student was like, "No, that's not right." And I was like, "What?" She's like, "Yeah, I had a 7th grade teacher who like made us memorize the first 10 digits of pi." I was like, "Wow, that teacher has too much time on their hands." But I approve. Let's see here. Natural log of 42 is 3.73766696. I'll just keep that many. Natural log of pi. So you do need a calculator for the next test for sure, right? Because there's going to be some decimal work in the next test that you need to be able to do. So you're going to need a calculator which can do these kind of calculations. Otherwise, it's going to be a problem. I'll just keep that many. So that's approximately I'll just give us the first. I get 3.2651 to the first, the four decimals there is like that. We good? Okay. So I want to shift over here now back to what we were more doing. Example 2. What's wrong with me? Goodness gracious. Example 6. So, so this is like number 9 in your homework, but number 9 in your homework is kind of dumb. It just says, I mean, number 9 in your homework is very, I don't know, whatever. So it gives you like A, B, C, D, E, F. You know, what's the best first step to solve this equation? Well, let's solve the equation rather than just take the first step, okay? So how would you solve this equation? What is the best first step? How do we solve something like this? What do we do? Yes, what we want to do is we want to take the natural log of both sides because that will get rid of the exponential. And so if we do that, lo and behold, we're going to have something that we can solve. See, because this gives us 5x minus 1 equals to the natural log of 20. Now the natural log of 20, it is what it is, right? It's some number. It's not terribly important what that is exactly. We can just leave it like that. And so this gives us 5x equals 1 plus log 20, which gives us x is equal to 1 plus natural log of 20 divided by 5. And so that's a perfectly good answer for, if this was a question on the test, I might want that as the answer. Right? On the other hand, I might say, give me the best decimal approximation to the answer using the first whatever, how many digits, right? So if we wanted to do that, then I go over to my calculator, I do 1 plus the natural log of 20, get whatever that is, 3.995, blah, 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 divide by 5. And so this is approximately equal to 0.7991. Okay? We do need to be able to do both, all right? We need to be able to both find the exact answer like I did in the box, and we also need to be able to find like decimal approximations like I did afterwards, okay? Both are important, especially for like science classes, right? Like if you had a course in physics and you end up with an equation like this and you're solving it, they're going to want the decimal number, right? Or chemistry or something like that. Let's see here. How about this one? Example 7. Suppose you want to solve this problem. 0.5 to the x equals to 9. How are you going to do that? So I think, I mean, again, we should just do what? So as a generic point of order, if you've got an exponential equation and you want to solve it, a lot of the time, the right move to solve it is just to take the natural log of both sides. So we can try that. Take the natural log of both sides. What happens? By property 2 that we proved at the start of today, that's x times the natural log of 0.5 equals to the natural log of 9, and then solve for x. X is equal to natural log of 9 divided by the natural log of a half. Right? And it's probably a good practice for us. What's the decimal of that, right? What's the decimal equivalent of that? Let's find out. So we got ourselves natural log of 9 divided by natural log of 0.5. That gives me minus 3.170. Okay? All right, so far, all of these ones we've worked so far have been kind of the same equation-wise. We keep finding ourselves solving the same sort of equation. Let's try to, there are other problem types out there. Let's expose ourselves to the other kind of monsters that are waiting in the wing to attack you. Let's see here, so this one is relatively benign, example 8. Well, okay, fine, this one, no, it's still the same problem. Just a second here, I'm trying to find something nastier for us. Here's a mid-level boss. E to the 2x. Actually, this is kind of like the worst that you guys tend to run up against. E to the 2x minus 14 e to the x plus 45 equal to 0. Now this is different. This is number 16. This is going to require a little bit different of an approach. How do we solve something like this? So what we're going to do here is we're going to make a substitution. See, we look at this and we go, well, that's really e to the x squared, right? Minus 14 times e to the x plus 45 equal to 0. So if we make a substitution, right? If we let y equal e to the x, then this is a quadratic equation in y. This is y squared minus 14y plus 45 equal to 0. Right? Hey, but we know how to solve those. Those are quadratic, right? And what are our weapons to solve a quadratic formula? We could complete the square, we could factor. Of course, factoring, chief among them, right? If we can factor, we do that. Can we? Can you factor this? $45 is what? 1 times 45, 3 times 15, 9 and 5. Hey, 9 plus 5 is 14. I think that might be the way. Let's just try that out. So y minus 5. Y minus 9, was it? Is that right? I think that works. Minus 5 times minus 9 is 45. And we have got minus 5 plus minus 9 is minus 14. There we have it. So this equal to 0. So what are my solutions then? Y equals to 5 or y equals to 9. Now, are those the solutions, though? That's the solution to the quadratic. We're not done, right? We're looking for x, a solution in terms of x. So what do I got here? I have, I've got e to the x equals to 5, or what? E to the x equals to 9. So how do I find x now?
You see which one equals 0.
Equals 0. Well, y equals 5 is going to give me 0. Y equals 9 is going to give me 0. The question is, how can I get 5 or 9 to be y? What x do I have to choose here? How do I solve what I just came to? How do I solve these? Now that I've got it back to x. I've got this problem or that problem, right? How do I solve for x there? So now we're back to a problem like example 5 or like example 7, right? We take the natural log of both sides. So natural log of e to the x equal natural log of 5, or natural log of e to the x equals natural log of 9. So the answer is either x equals log 5 or x equals log 9. And there you go. Them's your answers. Now you got to be careful with these problems. See, because when you get to the quadratic, right, there's no guarantee that the solutions you're going to get for your substitution are going to both be positive. This is nice. They were both positive. We get two answers, log 5 and log 9. If you had factored in such a way that you got a positive root and a negative root, you'd have to throw out the negative root. Because if you have a negative number equal to e to the x, you can't solve that, right? Like, I can show you another one of these. For example, if we had something like 4 to the x plus 2 to the x minus 2 equal to 0. See what that is 2 to the x. Well, it's 2 to the 2 to the x, yeah? Which we could rewrite as 2 to the x squared, yeah? That first term is 2 to the x squared. So what I've got is I've got 2 to the x squared plus 2 to the x minus 2 equal to 0, which would give me y squared plus y minus 2 equals to 0. If I make a y equals 2 to the x substitution, can you factor that? I mean, I think we can, right? This is y plus 2 times y minus 1, right? Do you guys see that? So I get the plus 2 and the minus 1. That gives me a plus 1 overall for the cross terms. And so then we find ourselves with either y equals minus 2 or y equals 1, right? Which means that we're solving 2 to the x, excuse me, e to the x, 2 to the x equal to minus 2, or 2 to the x equal to 1. So in contrast to example 8, this one only has one solution, right? Because this one right here, no solution. There's no solution to that because remember, one of our principal properties of the exponential is it's positive, right? The exponential is positive. We can't solve exponential equal to negative number. Try as we might, right? On the other hand, 2 to the x equal to 1. I don't need a calculator for that. Can you solve that one? What's 2 to the x equal to 1 have solution what? Yeah, this says x equals to 0. So this equation has just one solution, namely x equal to 0, which I think a lot of you might have guessed if you just had confidence to guess something, right? If you just look at that and you thought, wait a minute, 1 plus 1 minus 2 is 0, so yeah, x equal to 0 works. So this is called a quadratic substitution. So my point to you with the quadratic substitution is just be careful. Just because you get two solutions from your quadratic doesn't mean that you actually have two solutions. It could also happen that your quadratic has a complex solution, which means there's no solution, right? Or it could happen that your quadratic solution had two negatives. That also would be no solution, right? You could even have a repeated root. Like all of the different cases are possible for the quadratic if you think about it. So next class, I will continue forging ahead. We'll work problems that are like log equal to stuff. And anyway, there's time for homework questions this week. You guys just got to ask the questions, right? So anyway, go vote. I don't know. I feel like I'm supposed to say that. I don't know.